Yeah, that's good. Okay, so for the next talk, we have Owen Vermeulen from K11, students, and we will talk about HB stars, pulsating, breathing, and launching materials. You can go.
Yes, thank you for the introduction. So indeed, I will be talking about HB outflows and more specifically how we actually drive these outflows now in Phantom. So we already heard about HB stars yesterday from Camille and Sam. But just a quick recap. So HB stars are the evolved versions of low to intermediate mass stars, which have typical initial masses between 0.8 and 8 solar masses. And in this phase, which is one of the final phases, these stars strongly increase in radius, and so they also cool down in the outer regions. And also this phase is strongly characterized by this dust-driven wind, with typical mass loss rates ranging between 10 to the minus 7 to 10 to the minus 5 solar masses per year, and quite low terminal wind velocities between 5 and 30 kilometers per second. So how are these winds driven? This we also saw yesterday, but again, a quick recap. So starting on the very left, we have the HB star itself. It's still dredging up material and so enriching the outer layers. But the most important thing for this presentation is that these stars are also prone to very strong radial pulsations. And these pulsations are expected to levitate material up in the cooler regions. So the increase in density combined with the lower temperatures makes it then possible for dust grains to start forming. These dust grains are pushed outward by the infrared radiation from the HB star, and they drag along the surrounding gas, thereby initiating the steady outflow of material, or we call them dust-driven wind. We also saw yesterday a bit that we expected these stars to be quasi-spherically symmetric. However, thanks to recent observations where we can actually resolve these outflows, we now see a wide variety of complexities arise, for example, spiral arcs and even bipolar outflows, with then the main hypothesis being that this is caused by a hidden companion that is then orbiting in this outflow created by the HB star. Now, we have modeled this in the past within Phantom using the so-called P-wind approach. So the idea behind P-wind is that we simply inject particles into the simulation following some steady state wind solution. The idea is also that we artificially balance gravity, so we put this gamma factor to 1. So particles are not being de-accelerated, they're just injected and they're free to flow out of the system. Now, with this approach, we can also create some nice looking simulations. So I show here 3 simulations that I created last year for 3 different orbital separations. In the top, we have the orbital view, and the bottom, the echelon view, and we see always a very pronounced spiral arise in the orbital view. Whereas in the echelon view, we see some more arc-like structures arise. Now, what does it actually mean to use a free wind? If we take this picture once again, if we use a free wind, it essentially means that we're starting our simulations where a steady outflow from fluid is being created. Some models are already being generated where we also include acceleration upon dust. But in those cases, it is either on top of a free wind, or you need to inject particles with high enough velocities so that it actually reaches the point where dust is being created. So we now want to do this instead by driving them from pulsations. We want to push this all the way back to the star. So to do that, well, first you need something to pulsate into. So first we need to set up the atmosphere of these stars using some initial hydrostatic profile. And we only need the atmosphere. So in order to set this, I use Fibonacci spheres, which is basically just a way of equally spacing a random number of particles on a spherical shell. We want then to build this on top of boundary layers. So we assume the first 5 shells to be boundary layers shown in red. And these boundary layers, we then let them oscillate using the simple sinusoidal motion. And then what you get out is something that looks like this. Well, it's a bit more smooth on my screen, but you get the idea. So now we do not artificially balance gravity anymore, but particles are de-accelerated, they fall back, but then they interact again with the pulsation. And so this way we now can drive an outflow. This we then also combine with pressure on dust grains, because otherwise your velocity is too low to actually escape the system. But instead of doing the circulation theory or the other approach of dust, we just assume some simple opacity of dust using this prescription, which is called the Ohm prescription. But essentially, your dust opacity is just a function of the temperature. One caveat also of this method is, of course, that after some time, particles will start to escape the system, which means that subsequent shocks become less and less strong. So I implemented also a way that you can actually keep injecting particles to kind of offset the master's rate, so that you can continuously drive these pulsations. To visualize this, I have here two very low resolution models. They are identical in setup, with the only exception being that on the left, I don't inject particles whatsoever through the simulation, whilst on the right, I try to offset the master's rate. And after about 10 years, you can really start to see a difference, as there are way less particles close to the boundary on the left compared to the right. And so every shock wave becomes less and less strong. And yeah, it becomes way worse over time. So yeah, you really see the importance of injecting particles. Now, I haven't shown yet what this looks like in density. So on the left, I once again just show the particles, but on the right, slice the density. So the first shock is a bit of this transient behavior because you're pulsating into a vacuum. So it's a really strong expansion, but afterwards we see this creation of nice concentric shells forming, which of course correspond to your pulsation shock fronts. You also see that they're really quite visible, quite further out. And actually, if you go to a somewhat high resolution than this, you can see them even to 100 AU. That's quite nice. Now, of course, we also want to validate what we've implemented and also compare to what we had previously. So on this figure, on this slide, I show 3 different figures. And on every single one, I show first in blue a profile corresponding to the free wind approach we had previously. In orange, the pulsations within Phantom that I now implemented. And then in green, we also have a very similar setup in a grid-based code, namely MPIA MAVAC, which I always show in green. And then on the left, I show the density, in the middle, the temperature, and on the right, the radial velocity. So first of all, if we compare the profiles corresponding to the pulsations, we now see a very strong change compared to the free wind, especially if you look at the temperature and the radial velocity, where you now see these very nice shocks again forming in these profiles. But also if we compare the grid-based code to our SPH results, again, especially in the radial velocity, which I consider to be the most important thing when we look at also the direction of the binary star later, we really see that the results agree quite nice. In the temperature, there is some differences, but there is also some difference in how cooling is handled in the code, so it's not that weird. But in general, I'm quite happy with this agreement. Now, of course, everything becomes a bit more interesting when we add a second star. So I have 3 preliminary binary models to show. Now, these models are quite old, but I expect them to be almost the same in the most recent version. So first, I have a wider binary. So on the left, I always show a more zoomed in orbital plane, on the right, a more zoomed out version. And this is for, well, the orbital parameters are shown on the top right. So a separation of 8 AU for now circular and primary mass of 1.5 solar masses and a secondary of 1 solar mass. So on the left, we see that now the pulsation shocks are slightly deformed due to the presence of a binary companion. And in the more global view, we once again see this very pronounced spiral structure arise, but now superimposed with these pulsation shocks. So we see this nail-like pattern arise a bit on the right. This is even more pronounced when you also go to a closer binary. So now we have a binary at 4 AU. Transient, of course, of your first shock. But now, for example, you see a nice stream of material between the primary and the secondary. So also push up over a strong deformation of your pulsation shocks. And if you look just behind the companion, kind of see also how the pulsations interact with your spiral pattern, almost creating this fault-like pattern in your spiral arm. And then if you look on the right, you see that now the outflow has become significantly more complex. And we also have an accretion disk form actually in this one, which was not the case for the wider binary. Finally, I also have an eccentric binary. So again, 8 AU, but now with an eccentricity of 0.75. So the companion really grazes into the atmosphere. Again, after this grazing, you see the strong deformation of your pulsation shocks. Again, here an accretion disk is forming. And in the global view, we once again see a somewhat more complex structure arise. So I'll just let this play out for a second. So that already brings me to my conclusions. Well, I don't really have conclusions because I have mainly been implementing this rather than actually analyzing the models. But what we can conclude is already that pulsation strongly affect mainly the velocity and the temperature profiles of our simulations, and that we have a nice agreement with also grid-based code. And that this also can give rise to more complex morphologies. Regarding future work, of course, we wish to combine this also with the chemistry from Camille that we saw yesterday, and also the dust that David is working on. So tune in tomorrow for those results. And then the thing that I want to look at in the future is also how this impacts actually the output. In the past, studies have been done already, also with FDH code, but these always used a free wind approach. But now that we have pulsations, the mass transfer has also changed. So this can also greatly impact the output evolution. The last thing that I want to look into and implement is kind of mimicking this asymmetric wind driving that we actually observe in very detailed single star simulations. So here I show one example of single star simulation from Freitag and Owen, where you really see these very asymmetric blobs forming in the outflow, which is quite far from what I get with these very spherically looking spherical shells. So a way that I aim to implement this is by also deforming the boundary itself and letting that pulsate into the atmosphere, because this outflow is really driven by also convection, which I don't aim to implement yet. So with that, I like to thank you all for listening, and I will gladly take any questions.
Thank you very much, Owen. Do you have any questions in the audience?
This is a silly one, probably, but I don't know anything about the omega you used. What was it based on for the pulsations? Yeah, just yes, yes. Is there a
so it's just related to the period of your pulsations, which we can observe. Well, if you have very periodic pulsations, you can observe this. It's on the order of 1 year.
Oh, okay, 1 year. And the time for your simulations is comparable to that, so.
Yes.
Okay, good.
Question, there's that can go through.
Should go last, but amazing job, Owen, looks amazing. I was going to ask about the non-spherical thing, I mean, how you plan to do that, but also like, would it change much if you put the boundary further down? So if you imagine pulsating the star from further inwards, presumably you don't have to necessarily inject mass quite so much, or the same, or would it still work the same, or is it a special place where you're putting this pulsating?
So, well, physically, the pulsations arise from your ionization layer, which is a bit below the surface. But I find that it behaves almost exactly the same, no matter where you put your boundary. Your profiles come out a bit different, of course, because you've just shifted it a bit. But in general, I don't really see any big deviation from what I have now, and it just introduces another parameter that you can tune. So for now, I just take it equal to the stellar radius, because it doesn't change much.
Questions? In the meantime, you think about that. I have 2 remarks for you. The first one is that I'm really happy to see that you indeed such a fierce competitor into the movie competition. It's really cool, actually. The second one is very show and ambient interface. So when you do this comparison between the different codes and implementation, I expect also between the API code and implementation. So do you aware?
Well, in general, cooling is kind of annoying to implement in general, because even with these pulsations, because you're starting from a hydrostatic profile, if you just activate cooling, it just collapses. So I activate cooling based on whether the particle becomes unbound, and then I activate cooling that you can actually, well, see right there, cooling is activated. And in the grid-based code, that's not an issue. So they cool everywhere. So I think that already has an impact. And also the cooling functions used differ very slightly. But in general, I would say that the temperature is quite uncertain in both codes. So I don't think, that's why I like to focus on the radial velocity, because that's a bit more, yes.
Any other question then, Daniel, before I
But just to ask again, so you were talking about you were injecting particles and pulsating at the same time.
Yes.
So you showed it, but I still didn't understand how you actually did that.
Well, we can talk about it later as well, because I worked on it quite well. Because you don't really see it happening, but that's also the point. So I continuously almost inject particles. Like every 10 days, I inject like 50 particles. And so like that, you
Outside the boundary.
just outside the boundary and with the velocity of the boundary at the point that you're. So at the point you inject, the boundary has a certain velocity. So you inject them with that velocity as well, just outside the boundary. And you just want to continuously re-inject, because if you re-inject once a year, you're injecting like too many particles at once, and you see really this ugly density wave flowing outwards because of this injection.
This is randomly, or it's a ring, or what? What is it? Or shell?
It's the same shell, so it also a Fibonacci sphere, and every time I rotate it, because if you just keep injecting at the same time, you see a stream of particles, and you also know that.
And with that,